Hello, class. We're going to discuss electromagnetic induction. Below is an experiment created by Faraday to observe the relationship between magnetic strength and current. What he discovered is that when you change the magnetic strength, the current is produced. In the experiment below, Faraday only observed current measurements right at the instant the switch closed or opened. Below shows how a wire can produce current just by changing the magnetic field strength through moving a bar magnet up and down. The spacing of the blue arrows represent the strength of the magnetic field. The closer the arrows are together, the stronger the magnetic field is. In Figure A, the magnetic field strength is increasing and the current measurement is observed. Figure B shows the magnetic field strength decreasing and current measurement is still observed. Figure C, the magnetic field strength is constant and no current reading is measured. Another factor that produces current, other than the changing the magnetic field strength, is changing the area of the loop or coil. If the loop size increases or decreases, current will be produced. We call the combination of magnetic field strength and area flux. Please become familiar with the definition of flux, as I will use this word frequently throughout this chapter. So now I can say the change in magnetic flux creates or induces current. Therefore, a changing magnetic field induces an EMF or voltage. Faraday's experiment used a magnetic field that was changing because the current producing it was changing. The previous graphic showed a magnetic field that is changing because a magnet is moving. Below is how we calculate flux. The symbol we'll use is that phi, magnetic strength times the area of the loop, or the coil times cosine theta. Cosine theta is an equation because flux is defined as the perpendicular component between the area and the magnetic field. The unit for flux is called a Weber, or WB, also used as capital T times meter squared. Here's a picture showing where theta is located between the area and the magnetic field lines. So we only care about the magnetic fields perpendicular to its component. In the picture below, we have a coil turned sideways. Figure A, the flux is 0 because none of the magnetic field lines are entering the center of the loop. Figure B shows a few magnetic field lines entering the loop at an angle, so the strength is weaker because we only care about the perpendicular components. And finally, Figure C shows the flux at full blast, where all the magnetic field lines are entering the loop. If the loop is constantly turning, current is produced because flux is changing. Recall, change in flux induces current. If we measure the change in flux over time, we can calculate the voltage or EMF. Recall, EMF is actually the voltage of a battery. The letter N, capital N, represents the number of loops in a coil. The more loops induces a larger EMF. Now that negative sign indicates the direction of the EMF or current is opposing the flux. And what I mean by the current opposing the flux is that the direction of the current in these examples depends on the direction of the magnetic field it produces. So in Figure A, the flux is increasing because the magnetic strength increases. So the current will flow in such a way that its magnetic field it produces will point against the magnetic field lines produced by the bar magnet. Now in Figure B, the flux is decreasing because the magnetic field strength weakens, so the current will flow in such a way by following the right-hand rule where the magnetic field it produces points in the same direction as the field lines of the bar magnet. So it's like a balancing act between figure A and B, where the magnetic field created by the wire of that loop opposes the field lines in figure A, but follows it in the same direction in figure B, so that the magnitude of the current is the same for both A and B. It's just in opposite directions. So in this example, we have a square loop wire with side L, 5 centimeters, in a uniform magnetic field, 0.16 Tesla. What is the magnetic flux in the loop? When B is perpendicular, or when B is at a 30-degree angle to the area of the loop? And then what is the magnitude of the average current in the loop if it has a resistance of 0.0012 ohms, and if it rotates from positions B to A in 0.14 seconds? So we'll do part A and part B at the same time. The only difference between those two questions is that theta changes. So we'll plug and chug, and we'll get your answers for A and B. Notice that I needed to calculate the area for the square. Now for part C, we'll use this equation to calculate the EMF or voltage first. Just plug and chug to get 3.6 times 10 to the negative 4 volts. And then from there, we can use Ohm's law to calculate the current to be 0.03 amps or 30 milliamps. And which direction is current induced in the circular loop for each situation? So for part A, and the magnetic field initially pointing out of the page passes through the loop. If you pull the loop out of the field, the magnetic flux through the loop decreases because the area decreases. So the induced current will be in the direction of the external magnetic field to maintain the produced magnetic field outward. By using the right-hand rule, current will need to flow in a counterclockwise direction to produce a magnetic field pointing out of the page in the middle of the loop. For part B, the external field is into the page, the coil area gets smaller, so the flux is decreasing. Hence, the induced current will be clockwise, producing its own magnetic field into the page to make up for the flux decreasing. Here, the magnetic field lines point into the south pole of the magnet, so the magnet moves towards us, and the loop, the magnetic field points into the page and is getting stronger. The current in the loop will be induced in a counterclockwise direction in order to produce a magnetic field out of the page. For this part, the field is in the plane of the loop, so no magnetic field lines pass through the loop, and the flux through the loop is zero throughout this process. Hence, there is no change in flux and no induced EMF or current in the loop. Now, initially, there is no flux through the loop when you start to rotate the loop. The external field through the loop begins to increase to the left. To counteract this change in flux, the loop will have a current induced in a counterclockwise direction so that it produces its own field pointing to the right.